Hi, this video is going over the exam to review questions. And so feel free to fast forward to the parts that you had issue with, but I will start with, I'll just write question number one. We'll start with that one first. Classify each of the following compounds as a strong electrolyte, weak electrolyte, or non-electrolyte. So strong electrolytes and weak electrolytes, let's put over here. And then non-electrolytes, let's put over here. So let's start with non-electrolytes. Non-electrolytes are any molecular compounds. Any molecular compounds at all, with the exception of acids. Acids or bases are the one exception to this, but because acids and bases are going to be electrolytes. But any molecular compound, so you'll see letter A, acetone, because it has, remember, molecular compounds are nonmetals bound to other nonmetals. Acetone has just C, H, and O, so therefore that's why that's the non-electrolyte. Over here with strong electrolytes or weak electrolytes, these are going to be ionic compounds. Ionic compounds would be considered strong electrolytes. And then the rest is all about being acids or bases. Strong electrolytes will be strong bases, well, strong acids and strong bases. Whereas weak electrolytes will be the weak acids and the weak bases. And this is all about whether they give you free ions. So ionic compounds give you free ions moving because of they've dissolved and dissociated in the water. And then acids and bases also give you free ions because they also dissociate, but strong acids and bases give you lots of them because they completely dissociate, whereas weak acids only partially dissociate, so they only give you some. So hopefully that's enough to give you that hypochlorous acid, which OUS means that it uses the polyatomic ion that ended in "ite." So hypochloric acid is the acid formed with the hypochlorite ion, so therefore HClO. That's a weak electrolyte because it is not one of the 6 strong acids. Remember, there are only 6 strong acids. You should know them by heart. HCl, HBr, HI, sulfuric, nitric, and perchloric. And because hypochlorous acid is not on that list, that's a weak acid, so therefore a weak electrolyte. Ammonium chloride is a ionic compound, therefore it's a strong electrolyte, and calcium hydroxide is a strong base, and because it's a group 2 metal hydroxide. So all of that's in your notes, and that makes it also a strong electrolyte. All right, moving on to question number 2. Will a precipitate form when aqueous lead 2 nitrate? Lead 2 nitrate. Lead 2 means it's the 2+ form of lead. Nitrate, everybody knows it's NO3 minus, so therefore lead 2 nitrate is this compound here, and it's aqueous. Lead 2 nitrate and sodium sulfide. Okay, sodium sulfide. Sodium forms the Na+. Once again, metal, non-metal. So therefore it's ionic. Sulfide is the S2- ion, and therefore this compound would be Na2S, aqueous. And the question is, will a precipitate form? If so, write the complete molecular, complete ionic, net ionic. So we are going to partner swap the Pb with the S and the sodium and the nitrate. The 2 products will be NaNO3 and PbS. When you look at your solubility table, you will find that lead 2 sulfide is going to be a precipitate. It's going to be insoluble, and then all you have to do is balance the equation by putting a 2 right there. So that is going to be your complete molecular equation that you'll see on the answer sheet. And then in terms of the complete ionic and net ionic, That's the complete molecular. The complete ionic will just be you taking any of the aqueous compounds, so him, him, and separating out the ions from each other and representing them individually. So each ion will get an aqueous phase label. So this is, you're going to have one of the lead ions, you're going to have two of the nitrate anions. So you're basically representing the molecule as dissociated. You're going to have two of the sodium ions, one of the sulfide ions, and then continue the reaction, two of the sodiums, two of the nitrates, and then remembering that you never break up your precipitate because he is not dissociated, because he's not dissolved. And therefore, you leave him alone. And then once you have your complete ionic, you can identify your spectator ions. This is spectator, 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 spectator. And your net ionic equation will be you just writing everybody that's left over. So I'm not going to write it, but it would be Pb2 plus S2 minus yields PbS solid, and you'll see it remains balanced. If you did it right, it should remain balanced. So that is how you do this. And for that one, you obviously need your solubility rules, which you will, of course, have access to while you're taking the test. All right, question number 3. What volume of 0.128 molar HCl is needed to neutralize 2.87 grams of magnesium hydroxide? Hint, to neutralize an acid, a base with an acid, you need the moles of H plus to be equal to the moles of OH minus. That's true. You need that to reach the equivalence point, which is where you have the same number of moles. And so there you definitely need a balanced chemical equation. Anytime you have any reaction at all in any chemistry question ever, you have to have the balanced chemical equation. So if it's not written there, that's the first thing that you should do is write one. So if we have HCl, and we're reacting it with MgOH2, magnesium hydroxide. Actually, we don't really need the phase labels for the stoichiometry, so I'll just leave them out. Acid plus base yields water plus salt, and hopefully you know acid plus base yields water plus salt, so H2O plus MgCl2. It would be the salt that you get from partner swapping. Those give you the waters, these give you the salt, and Mg is a 2+, he's a 1-, so that gets you MgCl2. And then we just need to have the balanced chemical equation, which means we need to look at the salt first. And I've got 2 Cl's right there, so I'll get 2 over here. And then 2 H's and 2 OH's get me 2 waters. So that's just going to be the equation that we use for this question. So you just write your balanced chemical equation just to see what's going on. That's going to give you the stoichiometry so that you'll know you need 2 moles of this for every 1 mole of that. Okay, so what volume of 0.128 molar? So anytime that I see a molarity given as part of the question, unless I'm doing a dilution. You're going to use M1V1 equals M2V2. And that, in those type of questions, I leave the molarity just as the molarity. Like I leave the unit as a capital M. But this is not a dilution question. We're not diluting anything. There's no stock solution. What I always do, even in my mind, is I always think of that as a conversion factor. To me, molarity, 0.128 molar is 0.128 moles per liter, and moles of HCl in this case. And I just think of that as a conversion factor. And then I think about how can I use that to solve my problem. I will tell you, you never start with the conversion factor. That's never the first thing that you write. I mean, I know I wrote it, but kind of off to the side. In terms of my unit conversions or dimensional analysis, you never start with your conversion factor, which means you're going to start with the other number in the question, 2.87 grams of what? Of MgOH2. Now, thinking about what you have to do, we are trying to get a volume, a liters or a milliliters or something like that. So how can I get liters of HCl from grams of this? Hopefully you see that's a stoichiometry question because I'm given information about MgOH2, but my answer is about HCl, liters. So if it's a stoichiometry question, you have to do a mole-to-mole conversion. That's going to come eventually, that mole-to-mole conversion. I'm obviously not ready for it yet because this is in grams. So the first thing I need to do is convert this to moles, in which case I'm going to need the molar mass of magnesium hydroxide. So getting my calculator and a periodic table, magnesium 24.31 plus 2 O's and 2 H's. So 2 O's is 32, and then H is 1.008. So 58.326 grams is his molar mass. And then now I'm ready for my mole-to-mole conversion because now I'm in moles. So for every 1 mole of magnesium hydroxide, I will need, or I will neutralize or react 2 moles of HCl. And then hopefully you can see the mindset here. This is going to be my last conversion factor. See, I have it laid out in my mind or on my paper, but that's going to be my last puzzle piece. This moles per liter will go here flipped upside down. Do you see that the moles of HCl is going to cancel? And I will end up with my surviving unit being liters, which is exactly the goal. So now I have this set up here perfectly. And it's time for my calculator. And I got 0.76884, but with the sig figs in the question, there's 3. That rounds to 0.769 liters, and that is the right answer to the question. So this was a stoichiometry question. And in some ways, it dealt with molarity issues as well. The key here is that if it deals with a reaction at all, you have to start by writing the reaction. And it's stoichiometry because the information given about MgOH2 was going to be used to answer a question about a different species, HCl. And therefore, I needed that mole-to-mole ratio. All right, so that is how you do question number 3. Question number 4. Oxidation numbers. Okay, SO2. Oxidation numbers are, let me just write all of them. SO2, CO, Cl2, MnO4 minus, that's permanganate, As4, arsenic, and K2O2, which is potassium peroxide. Okay, so we need our oxidation number rules, which are here. You'll have, they're on Blackboard under course documents if you lost yours. But let's just go through these one at a time. I think the easiest one is this one. That is an element because there's no other type of atom besides arsenic there. So it's definitely a 0 on the arsenic. All the arsenic atoms have an oxidation number of 0. Beyond that, let's just start here. SO2. SO2 is a neutral compound. There's no charge written up there, so it's neutral, which means that all the oxidation numbers of all the atoms have to add up to 0. That's according to rule number 3. So after that, you just briefly check rule number 4 to make sure you don't have any group 1 or group 2 metals, which you don't. These are both non-metals, which means you use this table here to assign one of them, whoever has the highest priority. So as you're scanning your eyes down, you're going to see oxygen first. Oxygen will get a -2 oxidation number, but because there are 2 oxygens, both oxygens will get you a net -4, which means this has to give you a +4 so that they all add up to 0. So that's the answer to that question. That's the sulfur's oxidation number. Moving on to this one, same idea. This is a neutral compound, so they all have to add up to 0. You don't have group 1 or group 2 metals, so you just go straight to rule number 5. All of these are non-metals. So you want to assign whatever atom is first priority. So as you scan your eyes down that list, oxygen is first priority. He's a -2. Because you still have 2 more atoms to go, you want to assign second highest priority. So as you're going down that list, look for whether you see carbon or chlorine first. And what you'll find is that chlorine, which is a group 7A nonmetal, he's the next highest priority. He's going to get a -1. Now that you only have 1 guy left, it's time to satisfy the most important rule, was that making sure they all add up to 0. So there are 2 chlorines, they both give you -2. That's another -2 from him, so this carbon has to give you a +4, so that they all add up to 0. +4, -2, and then -1 and another -1 add up to 0. Keeping in mind there are 2 of these. All right, so that's the answer for that one. For this one here, MnO4-, they are going to have to add up to -1 this time. The sum total is going to have to equal the charge, since it's a polyatomic ion. Same idea. You're just running through the rules. You do not have a group 1 or group 2 metal, so you go here and you assign oxygen a -2. And then what you'll find is that manganese is going to have to give you a +7, because there are 4 oxygens. Each of them gets you a -2 for a sum total of -8. Manganese will have to give you +7, so that it adds up to -1. And then over here, this is kind of the trickiest one in a way. Well, it's not tricky if you just obey the rules. So it's a neutral compound. They're all going to have to add up to 0. However, as you're standing here, rule number 4 is going to actually have to be satisfied here. Rule number 4 is higher than rule number 5. 4 is a higher priority rule than 5. So group 1 metals, which potassium is, have to get a +1 oxidation number before you go assigning oxygen. So that gets assigned, and then when you only have 1 type of atom left, it's time to make sure they all add up to 0. So what does oxygen have to give you for an oxidation number, so that all of the atoms add up to 0, keeping in mind there are 2 potassiums and 2 oxygens. And oxygen's oxidation number will have to be -1. If you had to see it like that, there's 2 potassiums. You don't even have to think about how they're bound. But the potassiums are both +1. And so the oxygens both have to give you -1, so that they all add up to 0. Hopefully you can see that. So oxygen's oxidation state is -1, and that's how you do number 4. Number 5. Okay. The fizz produced when an Alka-Seltzer tablet is dissolved in water is due to this reaction. So let me go ahead and just write the reaction on the board. 3 sodium bicarbonate aqueous plus H3C6H5O7 aqueous yields 3 carbon dioxide gas plus 3 H2O liquid plus Na3C6H5O7. You'll notice here, I'm not asking you to write this, or I'm not asking you to come up with this reaction on your own. This is given to you. The first question is, what type of reaction is this? Hopefully you can see that with 2 aqueous reactants and 1 or more gas products, that is definitely a gas evolution reaction. Now, part B, in a certain experiment, 1 gram of sodium bicarbonate and 1 gram of citric acid, that's this guy here, this is citric acid, are allowed to react. What is the limiting reactant? So you'll see you're given 2 different amounts of the 2 starting reactants. Well, actually, it's the same amount, a gram of each, but 2 different numbers. And to figure out what is the limiting reactant, you need to run the 2 tests. Figure out which one makes the least amount of product. So we'll start with the 1.00 grams of the sodium bicarbonate. We'll start with that guy here. I'll just leave out my phase labels. My goal is to figure out how much product they make. So I'm going, that's a stoichiometry question. So I need to convert grams to moles. So let me figure out what the molar mass is of sodium bicarbonate. 1 sodium, 1 hydrogen, 1 carbon, 3 oxygens. 84.008 grams per mole of sodium bicarbonate. And now I'm going to have to figure out how much product they make. Obviously, there's 3 different products. You actually can use any of the 3 to figure out the limiting reactant. But since the next part of this question is asking about how much carbon dioxide will form, theoretically, that's the theoretical yield, I'm going to zero in on this one since that's what the next question is about. I'll end up saving time. So I'm going to figure out how much of the CO2 will form. That's going to be my product of choice. So for every 3 moles of the sodium bicarbonate, I will get 3 moles of CO2. And in the final question, you can see in the answer that I do want that theoretical yield in grams. I know I said how much carbon dioxide will form. I really should have been more specific. What mass of carbon dioxide will form? So let me go ahead and just immediately put this into grams. So carbon dioxide is 44.01 grams per mole. So I've got this all set up now. Let me figure out how much of the carbon dioxide this one potentially can make. Zero 0.524 grams. And now it's time to check the other starting reactant, the 1 gram of the citric acid. I'm just going to abbreviate that CA for the sake of time. So that's first I need the molar mass of citric acid. So let's see here. 3 hydrogens, 6 carbons, 5 more hydrogens, I'll just do those 2 separate, and 7 oxygens, 192.124 grams per mole. And now the mole ratio, for every 1 mole of that, I'm getting 3 moles of this. So for every 1 mole of citric acid, I get 3 moles of CO2. Once again, the molar mass of CO2, which I just know by heart. And now time for the math. I'm getting 0.687 grams. So now that I have these 2 numbers, I look at which one is smaller. The smaller number is the theoretical yield. And so the answer for the theoretical yield is 0.524 grams. This is a hypothetical nothing, okay? It was just part of figuring out which one makes the least amount of product, okay? So that's something real, theoretical yield. This is tossed out once we realize it's the bigger number. And then that means that this is the limiting reactant, and this one, the citric acid, is in excess. So I've answered all of these questions that were offered. Sodium bicarbonate is the limiting reactant. That's the theoretical yield. And now moving on to number 6. Aluminum sulfide reacts with water. So aluminum sulfide, I'm given words here. Aluminum is a 3+ ion. Sulfide is just the sulfur anion. So to get something neutral, we will have this formula. Reacts with water. Okay, it's not telling me any phase label, so that means I don't have to put it in there. To form aluminum hydroxide. Aluminum hydroxide. Aluminum is the 3+ cation. Hydroxide we know is a polyatomic ion, so that would be his formula. And dihydrogen monosulfide. Okay, I see prefixes. That means we have a molecular compound, and the prefixes are just there to tell me how many of each thing. So di means 2. Dihydrogen monosulfide, 1 sulfur. And so that is dihydrogen monosulfide. The balanced chemical equation. So those are all the species. Now I just have to balance it. I just go for who I see first. I just saw 2 aluminums. 2 aluminums, so I get 2 aluminums by going over here. Sulfur. I see 3 sulfurs. I get 3 sulfurs by doing this. And then here's another example. If you've got H's combining with OH's to get waters, I like to think about it as just Okay, how many H's do I get from this? I'll get 6 H's. I mean, I do this kind of in my head, but I get 6 H's because I've got 3 copies and this each gives me 2. And I've got 6 OHs here because I've got 3 in each and I've got 2 copies. So in my head, I think of this as like this, and I've got 6 waters that will come out of that because each of these will make a water. So you can really do that anytime that the water is on one side and then on the other side you have H's combining with OHs to get you the waters. That's how I usually do it. Okay, how many grams of aluminum hydroxide are obtained from 14.2 grams of aluminum sulfide? Hopefully you see that as a stoichiometry question because my information is 14.2 grams of aluminum sulfide. But my question is about grams of aluminum hydroxide. So this is stoichiometry, meaning you're going to need a mole-to-mole ratio. Can't do a mole-to-mole ratio while I'm still in grams, so I better put the do a gram to mole conversion. So let me get his molar mass. 26.98 times 2 plus 3 of the sulfurs. 150.17 grams per mole of aluminum sulfide. Mole-to-mole ratio. For every 1 mole of this, I am actually going to get 2 moles of the aluminum hydroxide, which is what the question is about. And if they wanted to know moles, I would be done, but the question asks for grams of aluminum hydroxide. So I've got one more step. I've got to get this moles into grams, which is another molar mass thing. So what's his molar mass? 26.98. For the aluminum, I've got 3 oxygens and 3 hydrogens. 78.004 is his molar mass, and there I have it all set up. Now it's just time to run it through a calculator. 14.8 because it's 7.5 and I want 3 sig figs grams. And that is what I got for an answer. That should be good. Moving on to the next question. All right, so that was question number 6. This is now question number 7. You have a stock solution. Immediately I see stock solution and I think dilution because that's the whole point of a stock solution is it's a concentrated solution that you get to dilute to make more dilute solutions. It's a way to not have so many bottles in your laboratory. You have a stock solution of 14.8 molar ammonia. I can already tell that's going to be my M1. That's obviously a molarity, but the stock solution is your more concentrated solution. How many milliliters of this solution, so I'm obviously solving for V1, what's the volume of this solution, would you need to dilute to make 1,000 milliliters of 0.250 molar? So this is just M1 V1 equals M2 V2. I'm diluting. And it's just a matter of plugging in the numbers. So 14.8 molar is M1 V1. I'm just going to solve for that. M2 is my more dilute solution, 0.250 molar. And I want to make 1,000 mils of it. And since this volume is in mils, that means whatever number I get here will also be in mils. And so you just have to solve it. So I just do the right side first. And then I divide both sides by 14.8. V1 is going to equal, and I want 3 sig figs, 16.9 milliliters. And I know that's the unit because that was the volume unit over here. And that is how you would do that one. Okay, number 8. $25 mils of a nitrous acid solution. Nitrous acid. That was not on your list of memorized. However, we learned how to figure out the formulas for many acids if they end in OUS or IC. OUS means that it involves the ite form of the polyatomic ion, in this case, nitrite. So this is the one that has nitrite in it. Nitrite was NO2 minus, so nitrous acid must be HNO2. Nitrous acid solution, that was, by the way, if you didn't catch that, we learned that when we talked about naming acids. It's also in chapter 3. If you didn't catch that, you can go learn it from the textbook. Is titrated. Okay, right there, I know I'm doing a titration. Even before I read the rest of the question, you cannot do a titration unless you have a balanced chemical equation, because you have to get the coefficients. So let's just figure that out first. Barium hydroxide. We know him by heart. Acid plus base yields water plus salt. The salt will be whoever I get from barium and nitrite. Barium is a 2+ ion, so that salt will look like this. Nitrite is a 1- anion. All right, so now I've got my species in place. Now balance it. 2 of the NO2s I can get by doing that. Barium's already balanced. 2 H's, 2 OH's give me 2 waters. And that makes a balanced chemical equation. Now you can do this any way you want. It's a titration. I will go ahead and just do it with the titration equation. MAVA over the coefficient of A. Remembering it, A stands for acid, B stands for base. Remember, this equation can be used as long as you are assuming you are at the equivalence point, which in our class we always will be. That's the only kind of context that you are going to be doing titration. So you can read the question. It says 25 mils of nitrous acid solution of unknown concentration. So that's the unknown. So actually I can already tell we're going to be solving for molarity of the acid. Is titrated with 0.125 molar barium hydroxide. That's his molarity. That's the titrant, the barium hydroxide. If the solution turned light pink, that's code for you're at the equivalence point, so we're allowed to use this equation. Okay, if it turned light pink, that only happens at the equivalence point. After 13.78 mils was added, that's this number, volume of the base. What's the concentration? So this is just a matter of plugging numbers in. Na is the unknown, molarity of the acid. Volume of the acid was 25 mils. If you read the question, it's right there in the first word. The coefficient of the acid is a 2. Molarity of the base, 0.125 molar. Volume of the base, 13.78 mils. Coefficient of the base, 1. And so how I would do this is the side that only, I would almost drop my units. You can tell that the molarity unit is going to be molar. So let me just deal with the numbers, 0.125 times 13.78. I usually kind of resolve this whole side of the equation first. And divided by 1, obviously the number doesn't change. So it becomes 1.7225. The part of the equation that doesn't have a unknown. So I always do that side first. Then I'll just multiply both sides by 2 to get rid of that number. So now it becomes, I'll just do it up here, molarity of the acid times 25 equals whatever this turns out to be, 3.445, and then divide both sides by 25, and we will get the answer, 0.138 molar, because of the 3 sig figs and the 0.125 molar. So that's why that is the answer. Question number 9. Question number 9, calculate the number of molecules. Okay, right off the bat, I just need to remember, if I'm actually calculating for the number of molecules, you're going to need Avogadro's number. Because remember, the unit of molecules, we don't use that often. The only way you're going to get the unit of molecules is to figure out the moles and convert that to molecules. So this is what we're going to have to remember we're going to need. That's the only unit, the way to get the unit to be molecules. So it's not asking for moles here, it wants molecules. So I'm going to have to remember that. In a deep breath of air whose volume is 2.25 liters, so I'm dealing with gases. I can already tell that. 2.25 liters is the volume. Body temperature. So if it's 37 degrees C, remember with gases that you have to do all of your temperatures in Kelvin. None of the equations are going to work if you keep it in degrees C. So I'm going to go ahead and add 273.15 to convert it to Kelvin. Okay, I'm not going to use the Celsius. I'm going to use the Kelvin. And a pressure of 735 torr. All right, we'll deal with that in just a moment. Okay, so remember in the gas video that I made, I think it was part 2 that I covered this. Anytime you are given 3 of the properties of a gas, you can always figure out the 4th. So V, T, and P are 3 of them. The 4th is N, number of moles. The way to figure out the 4th is to use the ideal gas law. It will allow you, anytime you know 3 of them, it will allow you to figure out the 4th. In this case, the 4th one that I don't know is N. So I'm just going to solve for N here at this level. So number of moles, and that will allow me to, my last step will be this, but I'll get with that in a minute. N is going to be PV over RT. So now it's a matter of plugging numbers in. Now, R, let me put that in first. R is 0.08206 liters times atmospheres over mole times Kelvin. And because those are the units in R, all of these units have to match what comes in R so that they cancel. So what that means is that because R uses atmospheres, which it always does, I can't leave this in torr. I actually am going to have to convert it to atmospheres. And the relationship between atmospheres and torr is that 1 atmosphere is equal to 760 torr. This is just a conversion factor. So I just used it like this so that I can convert. So let me go ahead and put that into atmospheres. 0.9671 atmospheres. That's going to be what I use for P here. 0.9671 atmospheres is P. Volume is in the correct unit. It's got to be, so atmosphere is going to cancel. Volume has to be in liters, and thankfully it is. So 2.25 liters. That will cancel out the liter unit in the R. Temperature, we already talked about, has to be in Kelvin, and that's because that's what shows up in R. 310.15 Kelvin, so that will cancel out the Kelvin unit. And so all the units cancel except for moles, and moles is the one that I want to survive. It's in the denominator of a denominator, which means it's going to show up on top. So just make sure you enter this in your calculator, do the top, 0.9671 times 2.25, and then when you divide, make sure you enclose this entire thing in parentheses. That is going to be essential, and that's a very, very common mistake that a lot of people will do. You have to think about how you're entering it in your calculator mathematically. Okay, so 0.08549 97. I don't want to round too much. But anyways, that's the number of moles. And then I'm running out of room, but if you just use this conversion factor here, you will see that moles cancels and molecules survive. So I'm going to take this number and times it by Avogadro's number, 6.022 times 10 to the 23rd, and you'll get the answer, 5.15 times 10 to the 22nd molecules. So I kind of ran out of room, but basically this conversion factor gets placed right here, and you'll get the right answer. And now moving on to number 10, the last practice question. And these are just practice questions. Obviously on the exam, it's not guaranteed that it'll be exactly like this, but for instance, if this is this question is about Boyle's law, expect maybe a Boyle's law or Charles' law or Avogadro's law, something like that. All right, 10, a fixed quantity of gas. Fixed quantity means N stays the same. Number of moles doesn't change. 21 degrees C, oops, this is number 10. Even as soon as I heard it was about gases, I immediately am going to think that degree C is going to have to go into Kelvin, 294.15 Kelvin. Okay, so I just added 273.15. All right, anyways, exhibits a pressure, so that's the temperature, The pressure is equal to 1.22 atmospheres and occupies a volume of 4.38 liters. Okay, what volume will it occupy if the pressure is increased? Okay, this type of question is not a ideal gas law question because you'll notice, yes, you're given temperature, pressure, and volume, but it's not asking you to solve for a number of moles. You could if you wanted to, but that's not what the question is. The question is asking you for what will the new volume be if you change the pressure? And that is a Boyle's law question. You have an original pressure and an original volume. You are then changing the pressure to 1.88 atmospheres. Notice I made that P2. That's like a before and after. And it's asking you for what is the new volume. So you have to recognize that this is a Boyle's law question. P1 V1 equals P2 V2. And remember, Boyle's law is only applicable when the other two things are held constant, N and T. So if you read the question closely, it says a fixed quantity. That means the number of moles doesn't change. And right there in the last parentheses is the whole temperature doesn't change either. So temperature is held constant. So actually I did this. I really didn't need to do it. That wasn't really, we just needed to know that it stayed the same, and it does. So I didn't really have to put that into Kelvin. So at this point, it's just a plug and chug. So P1 is 1.22 atmospheres. V1, the original volume was 4.38 liters. The new pressure is 1.88 atmospheres. The final volume will end up being in liters because that was the volume unit used over there. Go ahead and just put it into your calculator. And for a final volume, I got 2.84 liters. Before I move on to the next problem, or if there was another problem, I always think, does it make sense? What did I do to the pressure? I increased the pressure. If you increase the pressure of a gas, volume has to go down because pressure and volume are inversely proportional. So did the volume go down? Yes, it did. It went from 4.38 to 2.84. And that's just a good check. It will make sure that if you did something weird with the equation or the algebra or whatever, it sometimes can prevent you making mistakes. That is the end of those 10 practice questions. Hopefully that helped you. And if you didn't need it, then that's even better. But just keep on studying. Use the textbook. Use as many practice problems as I've given you. Make sure you read over your notes. I've given you practice problems in the notes. You can always rewrite them and see if you can do those again. Good luck studying, and hopefully this was beneficial.